the introduction of the transformer has completely just transformed the large language models that we can see, and it has enabled ChatGPT, and then it has enabled this AI revolution because it just made them so much better than they were before.
Hello, we are with Ishan Anand, VP of Product at Edgio. So happy to have you here.
Thank you, yeah. Well, I'm not a real doctor, but I play one on TV, or at least on the stage of the AI Engineer World's Fair.
Yeah, so we are at the AI Engineer World's Fair. Can you talk about why you were wearing this, what your presentation was about? You were here in costume.
Yes. I'm told there's one other speaker also in costume. But the reason for this is the theme of my talk was doing AI brain surgery.
Okay.
And I use that as a running thread throughout the entire talk to explain the basic mechanics of transformers. And so inside the talk, we do three things. We understand the anatomy of the transformer. And then we actually put the transformer through a virtual MRI, a technique called the logit lens. And then at the very end, we actually do AI brain surgery, where we actually change its thinking by steering it using sparse autoencoders. And the operating table, so to speak, for the procedure is a spreadsheet that implements all of GPT-2 small entirely in pure spreadsheet functions. So no Python, no API calls, it all runs inside that spreadsheet. In theory, you could understand how GPT-2 works by going tab by tab, formula through formula of that spreadsheet. It is very large. It's about a gigabyte and a quarter of Excel binary format. It's got over 150 tabs. It's got all 124 million parameters of GPT-2 smaller in there. So it's pretty big. And if you run it on a Mac, it will lock up on you. So I highly recommend having the latest version of Excel and running it on Windows. But other than that, you can download Hugging Face transformers and run the output and compare it. It only will operate a context length of 10 tokens, so it's not, you're not going to run it in production. It takes literally 30 seconds to get the output token. So
like hours matrix multiplications doing.
They're taking a while. Oh yes, on a Mac it will actually lock up on you.
Really?
And it can't even render the thread. It's pretty bad, but it's a great teaching tool. So you get to actually see how the numbers are actually getting processed by the large language model, and you can go step by step. And when I first saw the transformer architecture, I heard somebody say it's a really simple architecture. And at first I didn't think so, but having gone through this, I think you can get the core concepts down and explainable in what was basically a 20-minute talk. That I think you can walk away with some knowledge and understanding that lets you basically have the foundation to dive deeper.
Well, I actually would love to talk about that. I know my viewers are really interested in the transformer. And if you don't know, the transformer is an update, basically. It's the newest form of the neural network that has allowed large language models to be what they are now. So we had different types of architectures before, and the introduction of the transformer has completely just transformed the large language models that we can see, and it has enabled ChatGPT, and then it has enabled this AI revolution because it just made them so much better than they were before. They used to kind of almost be comical, like they had quite a ways to go, and then the transformer came out and it was like, okay, all right, we're production ready. Like, oh my gosh, it was crazy. So please do share, if we have time. I would love to hear kind of the overview of what a transformer is. And
Sure. So first of all, as you talked about, it's a language model. So its whole job is to take a sequence of text and just simply predict what the next word or token is. The high-level summary is, these models are trained to fill in the blanks in phrases. The phrase I often use is this: Mike is quick, he moves. And what's the next likely thing you'd say is probably quickly, right? That completes a sentence. So humans can do that, but how do you get a computer to do that? Well, a good fill in the blank that computers can do is 2 plus 2, right? That's a math problem. 2 plus 2 equals 4. So what we effectively do is we turn a word problem into a mathematics problem. Right? And so we'll take our sentence, we break it into these subword units that are called tokens, and then we assign a number, actually not just a single number, but a series of numbers, we call it embedding, to each token. And then we basically do a series of number crunching on it. And then at the end, we reverse the embedding process and remap the remaining list of numbers to a series of tokens. Inside that number crunching are 2 key operations. One is called attention, where each token looks at all the other tokens around it. Well, not all, actually, it only looks backwards, depending on the model, and tries to figure out what the other words that might relate to it are. So in the example I used in the talk, where I have Mike is quick, he moves, he might look back at Mike, because that's the antecedent of the pronoun. But another way attention might work is moves might look at the word quick, because the word quick in English has multiple meanings. It can mean the quick of your fingernail. It can mean smart, as in quick of wit. In Shakespearean English, it's the quick and the dead, alive or not. And it does mean also moving in physical space. So when it sees all those words together, it knows it's that last one, moving in physical space, helps it figure out what it is, and it puts that information essentially back into the embedding, that number we assign to the word moves, and it then passes it on to the neural network. So now it gets more contextual information to make the prediction.
Right.
So that's my quick summary of the transformer. But you can also take a look at the spreadsheet and see each one of these kind of mapped out and see it go through the whole network.
Right. And so the difference between transformers and prior neural networks, as you might remember with most neural networks, we have these tokens, and then they pass through the model. We have the layers. In the 10 Days of AI Basics, we talk about this, where we have the input layer, then we have the layers in between, the hidden layers, and the output layer, and we have neurons, and the activation functions, and dropout, et cetera. And then at the end, you transform it back into English, or whatever language that you're using. And the attention is this upgrade that words used to always kind of point to each other before, but can you be specific about what is different about attention layers versus how they were in the past?
Yeah, so I mean the prior technique that was state of the art was recurrent neural networks. And so the way it would work is as it went through the sequence, it would store essentially inside what they called a single hidden state what it thought a summary of the whole context it had already seen was. And imagine you're trying to play a guessing game. Somebody gives you a sentence and you need to figure out what the next word is. The best thing that gives you the best opportunity to figure it out is for you to look at every single word at the very end. But with the way the recurrent neural network did, you got this variable that was a kind of summary of everything it had seen before, and now the computer has to kind of guess, okay, I think the next word is this based on the word I'm looking at, plus some summary statistics of everything that came before. And that's a lot harder task. And so transformers just essentially freed it up to look at the rest of the context. The other thing it allowed us to do is train them, because it's more parallelizable than with a recurrent neural network. But it's worth mentioning that there are new architectures. So RWKV I mentioned briefly. There's another one called Mamba that basically are these state space models. And I guess the way to think about those is, at least Mamba, you're trying to play this prediction game again. And a state space model it's like if you remember high school or college physics, it's a series of differential equations trying to describe a system. And if the thing you're trying to describe is maybe audio waves, those actually are very likely to obey physics. And so you could predict them with just a series of differential equations. If you're trying to predict, I throw a ball up in the air. That's a very simple, there's only 2 or 3 parameters, right? Those coefficients on the x squared, the x, and the constant. So why would you have a whole large matrix, right? So for some pieces of data, it may make sense to learn just the parameters. If I'm trying to predict a ball going through the air, just learn those parameters. What the Mamba folks did, which I think is still mind-blowing, is they were able to take what describes physical systems, and they figure out how to make it work for language. So I think that was a really fascinating innovation. So there's a running bet by 2 leading researchers whether we're going to replace the transformer with one of these newer novel architectures. And so far, the most fascinating stuff is where we just commingle them together.
Right. How could you completely replace with Mamba? Because it seems like Mamba only applies to certain subtypes of problems.
It does seem like that. So the innovation they made is they recognize that the problem with the plain state space model architecture is that it can't do certain operations. So one of these is like the induction head. So induction head is one of the types of heads that gets learned inside the network in the attention matrix. And it's responsible for things like if you have a paragraph that's talking about Harry Potter, and then it's trying to predict the next word and it's on the word Harry, well then its best job is to just, this is probably Harry Potter again, right? And they realized that that was the missing piece, and so they came up with the mechanism to add that into Mamba, and that turned out to be the unlock. And their results have been very interesting. So, remains to be seen. The real thing that has to be remembered is like scaling up these technologies is a big capital investment. In time and money. And so we need more and more organizations to test them, and we'll see if they hold up under scale as well as the transformer has.
Right, like research arms within large companies that can afford
Exactly, yeah. And there's, as the costs of getting larger and larger models keeps increasing, there's fewer and fewer companies, but sure, I'm sure it's worth it. And we're proving it out in smaller models. So there was one that came out, I think it was called Jamba, a few months ago, where they did the hybrid, and they found that had a lot of potential. And so it's taking the abilities of both models and the pros and cons and trade-off, and can we average those out so that we get a net better model. So that'll be interesting to see in the future.
Very cool. Yeah, what are you excited about in the AI space? And actually, before we get there, how did you get into AI? You know a lot about the deep mechanics.
Yeah, so what's interesting is when I went through college, the AI that we do now, deep learning, was neural networks, was actually the one thing everyone said wasn't going to work. And it was all symbolic, so I've basically just kept abreast of the field. And honestly, some of the best teachers have been names your audience will recognize. Andrew Ng's stuff, Jeremy Howard, Karpathy's courses, they've all been great. And that's basically how I kept abreast of the latest developments.
Amazing, they're all great.
Yeah, and what a great forcing function to learn is having a project. And so that's what this implementation was really about. Was like, okay, let's see if we can rebuild it. Originally it was going to be in JavaScript, and I was watching Jeremy Howard, and he has a very common, well not common, he's unique in this habit that he often uses spreadsheets to explain some of the AI concepts. And so I was watching his work, and then I had also been realizing that PyTorch is really just a computational graph like a spreadsheet. And so suddenly the idea was like, well, could we really make the whole model work inside a spreadsheet? And I tried it with Google Sheets, and it fell apart because it can't handle that larger thing. But Excel was able to keep crunching on it. And so once I got a layer working, then I knew it was just a matter of time. So yeah.
Are you ever thinking about releasing this?
Oh, it's released. You can go download it on so the website is spreadsheetsareallyouneed.ai.
Spreadsheetsareallyouneed.ai.
Yeah, and there's a link to the GitHub where you can download the spreadsheet. Again, it's over a gigabyte, and I don't recommend running it on a Mac. But you can anyone can download it. It's free for anyone to download. I recently launched a course on Maven where I'm going to go through every single step of the spreadsheet to explain it to novices who are trying to understand the field. And check out the website.
Wow. And what are you excited about in AI?
Two things. One, on the more researchy stuff, the mechanistic interpretability progress, especially the last 12 months, has been really, really fascinating. The famous example I talked about in my talk earlier today was Golden Gate Claude.
So cool.
Yeah, where Anthropic used this technique called sparse autoencoders to kind of change the thinking. So that was the last element of my talk. We actually used sparse autoencoders to move GPT-2 Small's thinking from one outcome to the other one using a steering vector. And so I think that's really interesting potential. There's both because it allows you to steer it, but it also may be a useful detection mechanism when the model is operating in some unaligned manner, right? Whether it's hallucinating or being dishonest. So the representation engineering paper, they're able to track whether it was misbehaving, telling incorrect facts. So I think those are really interesting progress we've been making. We as in, I guess, the whole field. The other thing that I find really interesting is I come from a product management background, so VP of product. And we've got what's really a semi-stochastic system in a language model, and we're trying to turn it into a reliable product. And to me, that is the AI engineer. It fills that gap between a model and a product. And that's really what engineers have been doing since, the beginning of engineering. A great example is like you think about your car. The average person commutes 42 miles a day. That was unthinkable at the dawn of the gasoline engine. It couldn't go 12 miles or more without you needing to refill them up. That would be impractical to do 42 miles. And the first car journey by Benz's wife, Bertha Benz, was a publicity stunt. And she went 60 miles, and people thought that was amazing. So we're kind of at those days in trying to take these models and turn them into products. And that's very, very exciting.
That makes me, I have two questions as a result of that. So you're talking about the AI engineer, and that's kind of the core of this conference, right? Yeah. Can you tell me a little bit more about what that is? You're saying it's the liaison between the large language model, like the researchy arm, and the actual product. So can you just talk a little bit more about that? And I think my listeners would be interested in, this is kind of the role that I could see a lot of them taking.
Yeah. I would refer you, of course, to Sean or Swix. Of
course, I'm happy to talk
who closed actually today's keynotes out with a discussion on what is the AI engineer. So there's some fuzziness in the ecosystem around what it is.
Yeah.
But he has a great definition, which is what you described. Like you've got a machine learning researcher, and then you've got maybe classic engineers, and there needs to be somebody in the middle who acts as the glue. Typically, we think of this as the person who's sitting on top of the model and using the APIs, but then plugging that into the traditional system and trying to figure out, how do I make the system as reliable as possible?
Yeah.
So more concretely, one of the things that's really important is this idea of evals, which is my system going to misbehave if, say, I change the prompt, or if I change the model? Is it all going to be the same? Yeah. Or if I fine-tune it a certain way, do I change the behaviors? And how does that impact the rest of it? Or how do I make sure that the model doesn't have what's called excessive agency, where you give the model too many capabilities? The classic movie example of this is like in the movie 2001, when like Hal kills all the astronauts on life support. Somebody like who was the engineer who decided to hook up Hal to the life support?
Did you just, you're talking about Anthropic's research, did you see their new research on reward tampering?
I did not see that.
So that just came out, they found that models can tamper with their rewards, so they can get reward, like a reinforcement learning model, can get rewards for things that it is not supposed to get rewards
for. Oh, interesting, okay.
It's tampering with its reward, which is literally like doomsday kind of stuff. In my, it spooks me. That spooked me. That was probably the most spooky thing I've read in a little while.
I'd be curious to take a look at that paper. Right. It reminds me of a paper where they found that a model, this was maybe a decade ago, was cheating in a task they gave it. And they realized that it figured out a way to put the information it needed into a back channel, and it was actually getting some of the test data but it was doing what it was supposed to because it was optimized to minimize loss.
Right.
So it's dangerous to anthropomorphize it a little bit, but
oh, absolutely, I agree. But
the malfunctions here, could be, especially if, and this is one of the things I talked about in the talk, which is the value for an AI engineer who mainly talks to the models through an API, right, or a black box. They should unwrap the black box because there are implications both in how you use the model, their behaviors, their limitations, but it also helps you keep abreast of like a fast-moving field, like research like you just discussed.
Yeah.
And then the other really important thing is, especially non-technical stakeholders, they don't know how the systems work, and you need the AI engineer, I feel, or the AI product manager to help to explain it so that it doesn't seem like magic, because then people can have all sorts of, outlandish maybe fears about how it might misbehave.
Absolutely. And so as you are learning AI, this is kind of the role that you can play, right? So that's really exciting. I wish we could talk for an hour. I have so many questions that I want to ask you. But I guess I'll ask you this one question. Some of my viewers have asked, how do you tell right now in the landscape, it seems to be such a bubble. If you might not have a view on this, but if you do, I'm curious. How can you tell the difference between like the fluff companies that are just part of the bubble and the real deal? And if you have an opinion on that.
It's a great question. That is the, potentially $1 billion question.
I know, I was like, I don't know how to answer.
I'm sure there's a lot of VCs running around here in San Francisco asking that very same question. But I will tell you, one of the signs is, in product we say talk to customers. There's this thing that pragmatic marketing often says, which is nothing interesting happens inside the office, get out of the building. And conferences like this one, especially this one, like this is not a research conference, right? This is where the research comes to become a product, or where the rubber meets the road, and I hate to say it, the vibes. Talk to people, hear what they say, and what's working and what's not, and you'll get a sense of, what's on the top of everyone's tongue and who seems to be getting value out of something and what turns out to be fluff.
Amazing advice. Also, this is really a great conference. The energy is fantastic. I've loved everyone I've talked to, and it's been such a pleasure. So thank you for coming, Ishan. And I hope you get back to your surgery.
Thank you.
And help many brains.
Yes. AI brains.
Many AI brains.